Okay, so the free body diagram looks like this. So the weight is still pushing straight down. The normal force is perpendicular. Now we're talking about sliding down the ramp, which means friction has to point up the ramp. So that's mu s times the normal. And in order to get it to slide down the ramp, Q has to be going this way, and that's horizontal. The rotation matrix is, so we're still rotating to a coordinate system like this. So the rotation matrix is cosine theta, sine theta, negative sine theta, cosine theta. And so the new rotated weight is cosine theta, sine theta, negative sine theta, cosine theta, times 0, negative w. And we get values of negative w sine theta, negative w cosine theta. And then the new Q is the rotation matrix times, in the unrotated coordinate system, Q now is negative Q0, you know, that Q vector. And so you get negative Q cosine theta, positive Q sine theta. And so the free body diagram, not the free body diagram, Newton's laws, Newton's second law, says negative W sine theta, negative W cosine theta, plus negative Q cosine theta, positive Q sine theta, and then we have positive mu s n 0 plus 0 n is equal to zeros. So equation 2 says n is equal to positive W cosine theta minus Q sine theta. And plug that into equation 1 and you get minus W sine theta minus Q cosine theta plus mu sub s times W cosine theta minus Q sine theta is equal to 0. So minus W sine theta minus Q cosine theta plus mu s W cosine theta minus mu s Q sine theta is equal to 0. The ones with Q's in them are this and this. So get those, you know, move those the other side, and you get q times cosine theta plus mu s sine theta is equal to mu s w cosine theta minus w sine theta, I think. Well, and then I just flip the side. I think I skipped this step. It looks sort of confusing, but everything over here is really moved to this side of this equation. And then q is equal to w times mu s minus sine theta yes, mu s cosine theta minus sine theta divided by cosine theta plus mu s sine theta. Okay, so compare this with so this is to get it going down. To get it going up, we had q equals w sine theta plus mu s cosine theta divided by cosine theta minus mu s sine theta. That's to get it going up. And you can see that to get it going up, you have a bigger numerator and a smaller denominator, yeah. And so going up has to be a bigger force than going down. Any questions about that? Okay, then the last thing we have to throw in is when you buy any kind of screws, I mean, there wouldn't be anything like mathematically wrong with selling screws in terms of an angle theta, but that's not how they're sold. So we have to figure out how to relate values that are given to that angle. Okay. So the last thing is relate the angle theta to the given parameters for a thread. And those are, well, what we're going to be working with are the lead and the radius r. So the lead is the vertical distance. If you, okay, so say the sun is over here in this side of the hardware store. There was a tornado or something. And say you start on this thread and then follow the thread all the way around. The lead is how much higher are you the next time you see the sun? Okay, like the next time you get to that side of the screw, how much higher, how much altitude change do you have? So that's the lead. Well, yeah, one rotation, but here's so the reason there are two parameters that often are the same thing, but sometimes they're different things: the lead and the pitch. And some threads, like if you start over here and follow the thread around until the next time you see the sun, you don't end up at you don't end up going from here to here. You end up going from here to here. Those are doubled threads. You know what I mean? And the pitch tells you the distance, the vertical distance from here to the next one. The lead tells you the vertical distance from here until whenever you next get to that side of the screw. No, you're not with that? Okay, so yeah. So, okay, so if a bug starts here, follows the thread around until the next time they're on the right side of this screw where the sun is. What the change in what their altimeter says is the lead, and that's what we're going to use, okay? That also, for most screws, is known as the pitch, okay? But there are screws where not all of these threads are the same path, okay? So the bug would never get on this thread. And so if he kept going around, he would totally skip this thread and end up seeing the sun again here, okay? Then the lead would be from here to here, but the pitch would still just be from here to here. Yeah, on one path, right? What? Most are single threaded. But that's a difference you just need to be aware of. So that's the vertical displacement for one time around. So what are the units, the SI units for lead? Meters, I mean, it would be given in millimeters, but SI units would be meters. It's a distance. Yep.
So is there a convention to positive and negative lead for right threaded?
No, I don't think so. It's just given as, yeah, right. It's an absolute value, and you just say right-handed or left-handed. And now the radius is, I already showed that in a different picture, but the radius is from the center of rotation to the edge of the thread. Okay, so how do you relate these to the angle? Well, think of taking that thread and removing it from the screw and then straightening it out, okay? So so think of unwrapping the thread. Then what you have is a long incline like this. Okay? This is the lead. And what's the horizontal? It's related to the radius, but it's one circumference. So this is going to be 2 pi r. And that angle that you want then is the inverse tangent of the lead over 2 pi r. Any questions about that? Okay, so that's it for square threaded screws. And the right-handed and left-handed thing, I think that comes up in the practice problem. So that's question? Yeah, right. So right-handed threads follow righty-tighty, lefty-loosey. So that means that if you're looking at so if you're looking at either end of the screw, then you rotate it. You rotate the screw clockwise to make it go away from you. Okay. So if you turn it clockwise, that's rotating it right, like turning a steering wheel to the right, and that tightens it into the thing, makes it move away from you. Okay. And so here's the other end of the screw. Like, how do you know? I mean, how do you know which side is the side that works that way? Well, actually, if you sat on the other side, so if this was rotating clockwise on this side and moving away from this guy, another guy looking from this side would be seeing it rotate counterclockwise and moving towards him. So a right-handed thread, no matter which side you're on, obeys that convention, you know. A left-handed thread is just the opposite of that. So if you rotate it clockwise, looking at it rotated clockwise, it'll come towards you. Okay. So righty-tighty, lefty-loosey is for right-handed threads. That's an important thing to remember as an engineer, righty-tighty, lefty-loosey.
Sense electric first question.
Yeah, that's true.
Yeah, you're
Left.
left-handed.
What?
Is it easier to use left-handed screws? Yeah. You're left-handed.
It's pretty rare to see left-handed screws. Bicycles have all these weird, like, and they're like, they pop up in places where there seems like no good reason, but they'll have backward screws like that. But yeah, I don't know. I think of it as screws. Right-handed threads are threads, and left-handed threads are backwards threads. I've never noticed anything easier about. I mean, like when you're trying to turn it, like you're just applying a force on something. So if you want to apply a force with your other arm, just like put the wrench over here and, you know. Yeah, I mean, that's right. So I think that's why it is like if the natural motion of the machine would loosen a right-handed screw, then you put a backwards one in. But on a bike, it seems to come up in. I don't know.
Like settle, shouldn't they?
Yeah, you would think, but it doesn't. But it doesn't. That isn't how they're set up. I mean, at least as far as I can tell. Any good questions about any of this? You know, good. So let's do. Let's think about. So the next thing is bearings. We're going to go on to bearings. And there are two types of bearings that we're going to deal with. Thrust bearings and journal bearings. I guess I'll start with thrust bearings. And the idea here is, so if you have a surface, and say this is a cylinder that's in contact with this surface here, okay, and let's say that there is a force N applied to the surface. You can imagine that applying this force N to that cylinder increases the force between the cylinder and the surface here, right? And that increases the friction between these two. And so if you start this thing rotating with this force N holding those two together, that friction is going to make it stop rotating, right? It's going to tend to stop that rotation. And so to keep it rotating with a constant angular velocity, or to start a rotation, you have to apply a couple. Okay, and so if you are trying to get this to rotate at a constant angular velocity, let's say counterclockwise to somebody looking down this end of the cylinder, it's going to require applying a couple m that way. Okay, and so what we want to do is be able to calculate what that couple is. That would be clockwise, wouldn't it? I saw you doubting that. Yeah, you're right. Okay, so let's change the force. That's easier to change. Oh no, that's the worst thing to change. Dang. Okay, so the force goes that way. And then, oh, well, it doesn't even matter. It just, because I didn't even say which way it's going to rotate. I just said the word wrong. Okay, so if you're trying to get it to rotate counterclockwise, you'd have to have your couple going this way. Right? So that's for a rotation like this. So there are two questions, two ways you can ask questions about this. The first is, what's the couple that you'd have to apply to initiate motion? That would involve the static coefficient. And the second one is what's the couple to maintain a constant angular velocity. And that involves the kinetic coefficient of friction. All right. So let's do this for, so I'm going to do this derivation for a hollow circular cross-section. So the cross-section looks like this, where we have an inner radius Ri. Can't see that very well. And an outer radius Ro. And so what do we, okay, so what's going to go into this derivation? We're talking about a torque provided by the friction, right? And the friction force is going to be perpendicular to the normal force. Can we just, so the friction force is going to be the same at every one of these points, right? At every infinitesimal point here, like the normal force is all spread out uniformly, so the friction force is going to be the same. So is there some way that we can calculate the moment by just taking like a moment arm and multiplying it by the friction force? That'd be nice. But the problem is that every infinitesimally thin ring that makes up this cross-section has a different moment arm. You know what I mean? And so the way we're going to derive it is we're going to do it as an integration where we break it up into infinitesimal rings and calculate the moment produced by the friction on each one of those rings. Okay, can you sort of picture what I'm talking about? Okay, so if this is the problem, we're going to break it up into a bunch of rings like this. So this is our infinitesimal ring. This we're going to call the variable representing this ring's moment arm R. That's going to be our variable. How do we figure out the total normal force on this ring? Because that's how we're going to figure out what the frictional force is on this ring. Well, we know that the whole area has n acting over it, right? So think of breaking this up into, so we're going to think about that normal force as like a normal force per area that's constant, okay? Like a pressure, okay? So think of, so the pressure applied by the normal force. Is going to be the total normal force divided by the total area, which is n over, and then the total area is pi times, so the area of the outside ring minus the area of the inside, so pi r outer squared minus r inner squared. And now for an infinitesimal area, the increment of normal force applied on the infinitesimal area on that infinitesimal ring is the pressure times the area of that ring Can you think of a way to measure the area of that ring? The thickness is dr. So think about taking this ring, and actually this is a really common trick for integration of circular things, to come up with an expression for the area of that infinitesimal area. So think of taking this thin ring and straightening it out into a rectangle, a long thin rectangle. Well, we know the thickness. We can calculate the circumference in terms of r. And so dA is just going to be 2 pi r dr. Okay, so we end up with n over pi r outer squared minus r inner squared times 2 pi r dr. Pi's cancel, yep. So, so we got n, or 2n over r outer squared minus r inner squared times r dr. This stuff is all constants. This stuff is going to be our variable that we're going to integrate with. What's the next thing we have to know? We're trying to figure out the moment produced by this infinitesimal ring. That normal isn't the force that's producing the moment. The friction is, right? So if this is the amount of force, the normal force, then multiply that by the coefficient of friction, and that gives you the frictional force. You know what I mean? Anyone? So the increment of friction force is the coefficient of friction times the increment of normal force. And so that is 2 friction normal over r outer squared minus r inner squared times r dr. No, well, it does because the amount of normal force depends on the area, because we're assuming that the normal force is uniformly distributed. You know what I mean? So friction doesn't depend on the surface area as long as the normal force stays constant. All right, and then the last thing is, how do we go from the increment of friction force to the increment of moment? All this friction force is acting perpendicular to its moment arm. So the basic story is we just have to multiply this by its moment arm, which is r again. Okay, so dm is equal to r d force of friction, which is 2 mu n over r outer squared minus r inner squared times r squared dr. And so the final step is just integrate. M is equal to the integral for the radius going from r inner to r outer. And actually we have all these constants. Let's pull those outside. So 2 mu n over r outer squared minus r inner squared times the integral from r inner to r outer of r squared dr. Okay, so that's an easy integral to calculate, and you end up with 2 mu n r outer to the third minus r inner to the third over 3 r outer squared minus r inner squared. Okay, so again, you know, I just derived this general formula, but I don't think it helps you much to just plug stuff into formulas. So I'm going to want you to, for these problems, be able to take the numbers I give and go through this derivation of the couple. Okay, I mean basically you're gonna take whatever numbers are given in the problem and go through steps just like this to come to the answer. Okay, so I'll do an example problem next time, and then we just have to talk about journal bearing friction, and that's it. So feel free to bring questions next time about the test or problem sets or whatever.